Welcome to part 1 of the video on implicit differentiation. In this video we're going to talk about the idea behind implicit differentiation, and we're going to solve one example. What is implicit differentiation? Well, until now we only dealt with explicit functions. For example, the function f of x equals x squared. I call this function explicit because here we have f of x equals something. We have an explicit expression of the function. That is, given an x, we can calculate f of x directly. There are some cases in which, instead of an explicit expression like this one, we have an equation. For example, x squared plus y squared equals 25. In this case, we can solve for y in this equation, and we get that y equals the square root of 25 minus x squared. In this case, y is a function of x. And what implicit differentiation allows you to do is to find the derivative of y of x. In the cases in which you have an equation like this, and implicit differentiation allows you to do that without having to solve for y. That is, you don't necessarily need to know the expression of the function in order to find the derivative. And this can be useful because there are some cases in which solving the equation is pretty hard and complicated, and the expression that you get is very complex and not very useful. And there are some cases in which you cannot solve for the variable. So let's see with an example how this is done. Let's consider again this equation, and we're going to write y equals f of x to make it very clear that y is a function of x. Replacing this, we have x squared plus f of x squared equals 25. And now we need to do a notational distinction. When we write the y over the x, we're talking about a noun. We're talking about the derivative of y. And when we write d over the y, what we're talking about is a verb. Here it should be dx, not dy. In this case, we're talking about the verb. That is, we're saying take the derivative of what follows. This is just a notational convention or distinction. We need to keep this in mind in what follows. So let's return to our problem. We have this equation here, and this is an equality between two functions. So we can take the derivative to both sides of the equation, like this. We have that the derivative of this function equals the derivative of this function, and here we have the derivative of the sum of two functions. So we can separate the derivatives like this, and here we have the derivative of x squared, that's 2x, and here we have the derivative of a constant, that's 0. So we have this equation here. Now the question is, how do we solve this? How do we find this derivative? And the answer is the chain rule, because you have a composite function. You have f of x and then that function is squared. So the chain rule is really the secret of implicit differentiation, and it is really the chain rule what confuses people when they are learning implicit differentiation. If we apply the chain rule to this function, we get 2 times f of x, that's the derivative of the outer function, times the derivative of the inner function, that's f prime of x. So we replace this in our equation here, we get this. And now we only need to solve for f prime of x, because remember, we're trying to find the derivative of f. If we solve for f prime of x, here we subtract 2x from both sides, we divide by 2, and we get this expression of f prime of x. And that's it. That's it, because remember that we define f of x as y. So what we found is that y prime, that's f prime of x equals minus x over y. And we can verify that if we solve for y in this equation. We have this equation, and here we can apply the chain rule directly. If we apply the chain rule, we get 1/2 times 1 over this to the minus 1/2, that's it, that's this, times the derivative of the inner function, that's minus 2x. We can cancel the 2, and this equals y, so we get minus x over y. So you see that in this specific example, you can find the derivative of y either using implicit differentiation or explicit differentiation. And well, you can usually do that, but in some cases it's much easier to directly use implicit differentiation, because solving the equation is very complicated or even impossible in some cases. So that's all for now. Thank you for watching, and see you next time.